So, welcome to lecture 41, and we have been discussing in the last couple of lectures about the mutually coupled coils if they exist in a circuit, how to tackle them. And also we found out the energy stored in a system of coupled coils. Okay. So, for example, just to summarize this, I must tell that you should not forget this, that is, if there are two coils and dot markings should be there. There are some problems where dot mark independent of dot marking the problem can be solved. So, if a problem is giving like L1, L2 and mutual inductance between the coil to be M, and if the dot markings are not provided, then you are free to choose your own dot markings, that is what you do, and then you can suppose the current in this circuit is I1 and current in this circuit is I2 like this. Then I told that across AB I am essentially reviewing, summarizing the thing in a contact form, compact form, and it should be suppose these two terminals are A and B and these two terminals are C and D, and suppose they are connected to some other parts of the network, this side and that side, and suppose the current are I1 and I2 respectively. Then the point I want to make is this one. There will be two voltage source here across, suppose this voltage across the coil is V1, this voltage, polarities are important. You cannot write just V1 or some I1 without showing any directions of the currents or any voltage without any polarity, never do that. So, this is the thing. Now, then I told that look at the direction of the current for L1 part, it will be always plus here minus here, because I1 is entering, that is fine. L1 dI1 dt, that is there, and here there will be another source of EMF coming in, because second coil is also carrying current, and if through the dot current enters, then the dot this side the polarity of the instantaneous voltage will be also, this is plus, this is minus, and this will be M dI2 dt. That is the essence of the thing, like this, and this will be your points A and B. Got the point. So, I will write V1 t to be is equal to L1 dI1 dt plus M dI2 dt, like that, KVL. On the other hand, the second coil, if you see the CD terminal, C and D terminal, and I have shown the current to be I2. So, there will be once again two EMFs coming in, which are connected in series, and one thing is about L2, it will be plus minus. This is wherever current is entering, that becomes plus, self inductance L2 dI2 dt. But first coil is also carrying current. So, there will be another EMF M dI1 dt here, and through the dot current is entering. So, this dot, that is C towards side C, it will become plus, it will become minus. If suppose the same equations I want to do it in this way, suppose somebody says that okay, these are the two mutually coupled coils and this is L1 L2 like this, L1 L2 like this, mutual inductance between them is M, that is also fine, and suppose somebody says he has assumed current I1 in this direction and the current in this circuit is shown like this, I2 here. Okay. And suppose the voltage here, it is shown to be V1t. Suppose the voltage here shown to be V2t. I am just telling situations may be like this also, because current directions I can assume in any it is my choice, it can be this way, that way, but after I write down the decide upon the current directions, then I must be very consistent about the polarities of the voltages. So, in this case, once again, if you see, this is suppose A, this is suppose B, and this is suppose C, and this is suppose D. Okay, it is another example, same mutually coupled coils, but somebody has assumed current directions this way, voltage polarities this way, like this. Then what I am going to do? Now, the across AB, first let me write down, there is self inductance L1, and this will be of course plus minus L1 di1 dt. Self inductance, in whichever terminals current is entering, that will be plus, it has nothing to do with dot, like that. And there will be another voltage here, which will be M di2 dt. Now, what I am telling, if I remember this rule, through the dot current entering will cause a voltage with dot plus here. So, I can say if I2 is flowing, it is coming out from the dot, it is as good as telling minus I2 flowing this way, is not? This is the current entering through dot. Therefore, I will through the dot, this current is entering, this blue current minus I2, and therefore, dot will be plus. So, you are absolutely correct in writing like this, M d dt of, then you write minus I2. Got the point? This is the point I want to make. Therefore, I will remember only one thing, through the dot if current enters, the other dot terminal will become plus, provided these two coils have got mutual inductance M, and then this is the circuit. But here you show it like this, which is exactly same as, this is equivalent to writing, because this is minus M, this is what, minus M di2 dt, it will be like this, treat this, but polarity you write like that, and then you can say okay, this is then plus L1 di1 dt, and then this is minus this potential of this point with respect to this is minus this quantity. Therefore, you can also reverse this polarity and tell that this is M di2 dt. So, either of them is true, and this is I1 for this problem I am doing. So, this is your AB, A and B. Then you say V1, which is here, V1, you say that it is equal to L1 di1 dt minus M, minus, because plus to minus, then minus to plus, therefore, minus M di2 dt. What about CD terminals here? Let us draw the diagram across CD. Across CD, this is your C, this is your D, and I have already pointed out this is my voltage polarity, applied voltage, and then this coil will have two EMFs. One is because of self inductance, another is because of mutual inductance. Now, the current direction has been assumed to be like this I 2. Therefore, so far as the self inductance is concerned, it will be L 2 d I 2 dt without any problem through whichever terminal, that is this way, no, not this one, this way I 2 is flowing. Therefore, it will be L 2 d I 2 dt, and then because of mutual inductance, the polarity of this voltage through the dot minus I 2 is entering. Therefore, dot here will become plus. So, that I write plus minus, and then you write here m d dt of minus 2 minus I 2. This is minus I 1, through the dot I 1 is entering. So, I am sorry. So, m through the dot I 1 is entering. So, it will remain m d I 1 dt, d I 1 dt. Here ends the matter, and the KVL equation, if you apply V 2 t, will be equal to L 2 d I 2 dt, d I 2 dt minus m d I 1 dt. Once you are accustomed with this one, you need not go to all the steps. Mentally, you can write down correctly the polarity of the voltages induced due to mutual inductance and self inductance, whatever be the direction of current chosen and things like that. That is what I told. And next time, next part what I did is, if there are two mutually coupled coils having mutual inductance m between them, with for a change, let me write this way, mutual inductance, and this is L 1, this is L 2, and if at any time the current through the coils are known, then energy stored will be equal to, instantaneous energy stored will be equal to half L I 1 square plus half L I 2 square plus m I 1 I 2. This should be remembered. Energy stored in a coupled coils will be like this. So, this will be the magnitude of the energy stored in the system. We have found out last time. Now, as I was always trying to tell you that these equations, whatever we have written is a general equation and in time domain. For any voltage V 1, V 2 applied to both the coils, in time domain I will be able to find out the currents if the voltages are known, because I know how to solve differential equation. That was there. Now, there is another source, as I am telling you, do I get, and if the sources are DC, of course, there will be no induced EMF either in terms of self inductance or in terms of mutual inductance, and these 2 points can be shorted. For DC, it is very simple. Although coils may carry current and they will just store energy, that will be there, stored energy will be there, but there will be no voltage drop across AB and CD if I 1 I 2 happens to be constant values, because that d I 1 dt, d I 2 dt, all things vanish to 0. So, that was there, but another important source, if you recall, what if we are interested to know steady state current, when the excitations are sinusoidal in nature, excitations or input are sinusoidal in nature. For example, that is, suppose some voltage is sin omega t. This sort of voltage is applied, then what is the thing? You recall that we have with single energy storing elements or multiple energy storing elements having no mutual coupling, we have seen that for example, an RL circuit, recall that if you have excited with a sinusoidal voltage source plus minus R L some V max sin omega t, we have done this problem earlier. In that case, it can be transformed into, it can be solved as a phasor notations plus minus the supply voltage will have some RMS value 0 degree. We find out that, and then R is to be replaced by R, no change, and this omega L you write it as j omega L, and find out the phasor current, and from there you can come back to the time domain to find out the steady state current in time domain. That can be always done, we have seen that. Whether such a thing can also be applied to a mutually coupled coils? The answer is yes. Why? I will just tell you like this. See, in time domain the equation is L di dt is equal to your supply voltage V s t, is not? Suppose this is your V s t. This is the circuit, and in this case the equation is R into I bar plus j omega L into I bar is equal to V s phasor, is not? This is the equation. Now, if you see from this side to this is the steady state solutions, mind you. Steady state, if you are only interested in, you can do. So, it is you can easily see this time domain expression. If you put replace d dt, this operator, by j omega, you get this equation. And these small letters which are real quantities in time domain, they are replaced by phasors. So, any differential equation can be translated into corresponding algebraic equation when the sources are sinusoidal in nature very easily. Wherever d dt is there, put j omega, that way you can always think j omega, you replace d dt by j omega and V s like that. Therefore, in mutually coupled coils also this can be done. Why not? Suppose you have got two mutually coupled coils, say with mutual inductance M between them, and this is L 1, this is L 2, this is V 1, this is suppose V 2, and suppose these are the currents I 1 t and this is I 2 t. And we have seen that across V 1 t, right now we have seen plus minus V 1 t will be equal to L 1 d I 1 d t, and then here also it is plus minus m di2 dt. Through the dot entering, that dot is plus. This is the equation which V 1 t is. So, V 1 t is equal to L 1 d I 1 dt plus m d I 2 dt. It is like this. Therefore, the corresponding phasor relationship will be V 1 phasors will be equal to L 1 d dt u replaced by j omega. So, j omega L 1 and current is I 1 phasor plus d dt into m j omega m into current phasor I 2. That is what I want to tell you. So, if the excitations are sinusoidal and you are interested only to know the steady state current, then you can straight away go to frequency domain like this phasor domain and write down the equation, solve for the current phasors and get the current. Similarly, for the second side, it will be equal to V 2 t will be equal to L 2 d I 2 dt d I 2 dt, is not, plus which I am not drawing that equation. We have come all the way several times with that thing m d I 1 dt. And if input is sinusoidal, you cannot do for all the any type of signals. V 1 t, V 2 t must be sinusoidal. If input is sinusoidal, then replace d dt by j omega and quantities in phasors. So that you will get V 2 phasor is equal to d dt, this d dt operator into L 2 becomes then j omega L 2 and small I 2 I will not write phasor, plus similarly it will be j omega m into current phasor is I 1, like this. Therefore, all the coupled coils, if the inputs are sinusoidal, we can write in the same way, replacing d dt by j omega. Okay. Therefore, this finally what essentially I mean is this: if suppose you say here the voltage applied is phasors plus minus, and this current you have shown to be current phasor dot, and the other side this is also dot, this is mutual inductance, and this current you have shown to be current phasor I 2, and this voltage is plus minus suppose V 2 bar, all are phasors. Then I will say that okay, V 1 bar straight away, it is not true that you write down in time domain then come to phasor domain, not necessary. If you are only interested in steady state current, I will draw like this all the quantities in phasor forms, and then I will say V 1 bar will be the self inductance j omega L 1 into I 1 phasor. Is not? Two sources will be there. Then I 2 is entering through dot, all other polarity those constraints will be there. Through the dot I 2 bar is entering. So, the upper one will become plus, but for d dt it is j omega only, and then m and then do not write small I2, write this one. Similarly, the KVL equation on the secondary side, this coil, it will be V 2 bar is equal to j omega L2, L2 L1 are the self and mutual inductances, j omega L2 into I2 bar, and then it will be j omega m into I1 bar. I1 bar will have a say in the induced voltage in the second coil, because these two have a mutual coupling. Where it should be, plus or minus? Yes, the upper one through the dot I1 is entering, it will be plus only. This is the thing I wanted to tell. Therefore, steady state analysis, when the input signals are sinusoidal, the corresponding phasor equations also can be written straight away, and please practice it to write it correctly. And when you will be able to write the equations correctly, when polarities of the voltages have been shown very clearly, which one is plus, which one is minus. Similarly, directions of the current phasors are shown with these arrows, then only you will be in a situation to write down correctly the KVL equations in different loops. Then of course, you solve the circuit to get the currents, and if you wish from phasor to come back to the time domain circuit, we already know it is nothing, you can immediately do it. Now, only one last point I want to make with this mutually coupled coils, which till now I have not pointed out, but it can be shown like that. For example, I have told you that when you pass this information one should know. In time domain it was like this, I1, suppose this is I2, this is suppose dot dot, all these things are fine. I told you that L1 is equal to N1 phi T1 total flux linkage per unit current I1. So, this is the self inductance. In time domain, if it is, it will be that instant value of current, but L1 value will be like that. Now, suppose you assume okay, constant values are flowing, this is I2, this is I2. So, this is the total flux linkage, of which N1 by I1, and this I broke up into two components, mutual flux plus the leakage flux. Leakage flux is not going to link the second coil. So, this is what we have done. This is the mutual flux phi M1 and this is the leakage flux phi L1, is not, only links the primary. So, that way I have done. Now, this leakage flux, if the coupling of the coil is very tight, no leakage flux, then phi L1 will be 0. In fact, phi L1 will become only a percentage of the total flux created. So, one can say that L1, if leakage flux, suppose some percentage of total flux created, then K1 bar is a small number, is a small number. How leakage flux can be reduced? If you bring these two coils in close proximity and things like that, then leakage flux can be reduced. But anyway, suppose it is some K1 bar will be a number, say 0.01, 10%, maybe further less than that, 5%, 0.05. And similarly, going to the second coil, I can say the leakage flux of the second coil will be some percentage of the total flux created by the second coil. Phi T2 is the total flux. So, this way it can be written. Now, if you recall that L1 is equal to N1 phi T1, that is what I have written here, divided by I1, I have written this. Now, this can be therefore written as, in terms of this leakage flux, some K1 bar N1 into phi T1. Phi T1 is the total flux. Okay. So, this is the thing. Okay, I am sorry. What I wanted to tell you, L1 is N1 phi T1 by I1, and it can be written like that. Similarly, okay, let us write like this. Similarly, you can write L2 is equal to N2 phi T2 by I2. This is there. And what is this? This mutual inductance is N2 phi M1 divided by I1, which is also same as mutual inductance calculated from the other side, that is N1 phi M2 divided by I2. Both all are correct here. Now, this is the thing. Now, if you multiply these two, that is L1 into L2, if you multiply these two equations, this and this equation, you will get N1 phi T1 by I1 into N2 phi T2 by I2. This is what you will be getting. And this can be written as N1 into divided by I1 I2. I can write. Should I assume this as it will correct na everything. So, N1 N2 by I1 I2 into phi T1 into phi T2, like this. Now, this can be written as N1 N2 by I1 I2, and phi T1 is nothing but phi M1, phi T1 is phi M1 plus the leakage flux phi L1. And phi T2 is phi M2 plus the leakage flux of the second coil, like that I can write. Okay. Now, this computation, what I wanted to show is, I will rather to make matter simpler, leakage flux will be a certain percentage also for mutual flux. Phi L1 can be this is 1 minus K1. Suppose this factor, I say that I am sorry, you please, this is 1 minus K1, it will be doing. So, K1 bar So, this becomes this is the mutual inductance term. Now, in terms of this K 1, it can be easily written as you can see that this M can be written as N 2 by I 1, M 2 by I 1, and phi M 1 is phi T 1 minus phi L 1, is it? This is the thing. This will be your phi M 1 for that, but phi L 1, as I have told you, it is nothing but N 2 by I 1, and this is then 1 minus K 1 bar into phi T 1. Similarly, from the other equation, that is M is also equal to N 1 phi M 2, N 1 phi M 2 divided by I 2, and this can be written as N 1 by I 2, and phi M 2 is total flux phi T 2 minus the leakage flux, which is a fraction of the total flux phi T 2, and this will be equal to N 1 phi T 2 divided by I 2 into 1 minus K 2 bar. This will be the thing. Now, what I will be doing is this step you just forget. It is not. Now, this is equal to M. M is equal to this as well as this. That is, concentrate on these two equations. One is so M can be written as M can be written as N 1 phi T 2 by I 2, N 1 phi T 2 by I 2 into 1 minus K 2 bar. Also, this is equal to N 2 phi T 1 by 1 minus K 1 bar. What is K 1 bar and K 2 bar? They are the percentage of the total flux which becomes leakage flux. Recall that phi L 1 is equal to K 1 bar into phi T 1, and leakage flux of the second coil is K 2 bar into phi T 2. Now, what I will be doing, therefore, I can write M square multiply these two, and you will get it as N 1 N 2 by I 1 I 2, then you will get 1 minus K 2 bar, 1 minus K 2 bar into 1 minus K 1 bar, and then you will get phi T 1 phi T 2, that is what you will get, which can be easily written as 1 minus some K 2 bar into 1 minus K 1 bar is equal to N 1 into multiplied by N 1 N 1 phi T 1 by I 1 into phi T 2 by I 2, and these are nothing but your 1 minus K 1 bar into L 1 into L 2. Now, this particular thing, these are numbers less than 1, and this can be written as some k square into L 1 L 2, or we say that mutual inductance will be take square root is equal to L 1 L 2, where k is called the coefficient of coupling, where k is called the coefficient of coupling. It will be a positive number, and k should be, for a tightly coupled coil, this should be close to 1. Mind you, k 1 is very small. So, 1 minus k 1 will be close to 1, this will be close to 1. Of course, you are multiplying once again, it becomes less than 1, but this is the thing I wanted to point out. Therefore, what we have done is mutually coupled coils, if they are present, if you know the coefficient of coupling and the self inductances, which by measurement it can be found out, then M can be evaluated like that. And not only that, if such mutually coupled coils are part of any circuit, I will be able to write down the KVL equations correctly, provided I know the dot conventions both in time domain as well as when the inputs are sinusoidal in terms of phasors, and we can solve the circuit. Thank you.